So good afternoon, everyone, and we are now going to continue with our symposium. So we have a talk now by Dr. Ashok Vudayagiri, who's come from University of Hyderabad. So Ashok actually did his BSc from Bangalore University, his MSc with specialization of quantum optics from University of Hyderabad. He then continued to do his PhD over there at University of Hyderabad in electromagnetically induced transference. And then he did a few postdocs in TIFR Bombay, Rice University, Texas, and RRI Bangalore. So he joined the University of Hyderabad as a faculty member in 2006. His research interests are laser cooling, quantum optics, and quantum information. So welcome, Ashok. We are looking forward to that.
Thank you very much. So the idea of I'll go a little faster because I have a lot of things to say. Measurement of time is always the interesting thing, and so measurement of time is always important at several stages. One way is to Earth rotates, so day and night, and other thing is to Earth goes around the sun, so one full year, seasons of course in between, all those things. But we are talking of time measurement at a much smaller level, like hours, minutes, and then a lot of convention, probably starting with Babylonians. Earth's rotation was divided into 24 hours. Indians used a slightly different time. Different parts of India use different time things. One is of 8 praharas, 4 in the morning, 4 in the afternoon. Sorry, 4 in daytime, 4 at night time. That's why afternoon you still say dopahar. Second, after 2 prahars, the third prahar is the afternoon. So that's how it goes on. But then measurement of hours, minutes, seconds started becoming more and more important. And of course, different people use different techniques. Water clock, probably Egyptians started it. Fill tank with the water, a little hole there, and then it starts pouring out to make measurements. This is one of the Egyptian systems. Egyptians also did sundials. As the sun moves, the shadow keeps going on the rotating on the platform to make a different. Of course, hourglass came somewhere around somewhere in the Renaissance Europe. Renaissance in Europe started around 1300, 1400 AD. So then they started making this hourglass where sand will slowly fall into the second one, and after that you can turn it around. Indians also probably used water clock. There are 2 kinds of water clock. One was where you fill a tank with water and the water flows out. This was a slightly different thing where you have a large vessel filled with water and you take a smaller vessel, make a small hole in it and keep it floating. And because of that hole here, water starts coming in like a boat, bad boat, and after some time water fills and then the entire fellow goes in. The Sanskrit word for pot was ghata, so this time taken was a ghatika because of that. A little apocryphal story associated with this kind of a thing. Truth of that we don't know. The story goes that a guy called Bhaskaracharya, around 1100 AD. He was both a mathematician, very well-known mathematician, and also a Jyotishi who could write horoscopes, and he wrote horoscopes for a lot of people. His own daughter's horoscope he wrote and said she'll become a widow very soon, but unless he makes a wedding in a very auspicious time. So he made one such thing to keep a auspicious time. But what happened? Lilavati was a child who was looking curiously at this, and when her necklace broke, one little pearl went and got stuck over there. It changed the rate at which water flowed. So the time measurement actually changed, and what he thought was an auspicious moment was not an auspicious moment. And then, so the horoscope became true. She becomes a widow, comes back, And then he tries to cheer her up in the only way he knows, which is he tells her lots of math puzzles, little math puzzles, and that's how the book Leelavati is supposed to have come. We don't know the truth, but this is somehow the story that goes on behind the book called Leelavati. It's a beautiful book with more than 130 math puzzles, each written in a nice uh, poetry form. Okay, but all somehow associated with this called Ghatika Yantra, and so that's what it was. Then we get a big shift. I'm told that somewhere in Jaipur there is still one Ghatika Yantra running in some Jain temple. I don't know which one, but anyway. So Galileo comes at around 1564. A lot of people wrongly think that he invented pendulum clock. No, he didn't. He discovered laws of pendulum. There are three laws of pendulum, very important ones. The first thing is that the period does not depend on the mass. Second is that the period does not depend on the angle that you are pulled back. And the third one is, as far as Galileo was concerned, period depends only on square root of length. Okay, he didn't know the full formula. That we had to wait till Newton because he didn't know G and all that stuff. It's Newton who came around and made a full calculation to give 2 pi square root of L by G. But Galileo had only up to this much, but this became very important. It really meant that the period of pendulum depends only on the length of the pendulum and nothing. That was a very important thing because there are a lot of errors in either in the mass or in the theta. Now this guy, his name was Huygens, the same one whom you know in your optics theory, the Huygens wave theory. This is the guy who used the pendulum to make a pendulum clock. Okay, this is the first guy. He's a Dutch guy. He made this, and how it worked in his time is this. This is an experiment some of us have done in BSc. We have taken a wheel, and then we have wound a flywheel, and we have wound a thread around it and put a weight. Because the weight wants to go down, the flywheel starts rotating. So think of a similar system, but a lightweight flywheel. But the flywheel, this also now think of it like lots of tooth. Okay, so the flywheel wants to rotate. Below the flywheel, I'm going to hang a pendulum. The flywheel has all these tooths. Okay. Now what happens is the pendulum is set into oscillation. This is the point at which it starts oscillating. It goes this way, and mic is off.
Yeah. Like
No. This red light is coming and going on. Red light's off.
yeah.
Okay. Good. So this is the wheel, and the pendulum below it keeps oscillating. And as the pendulum oscillates, what you will see is that it goes and sticks there over there, right? And when it sticks there, it doesn't allow the wheel to rotate. Okay, and then again pendulum goes back. Now the wheel is free to rotate. Again the pendulum goes that side. Again it stops the wheel to rotate. So the wheel can rotate only when the pendulum is during the swing. At the end points it doesn't rotate. So now imagine a pendulum which takes 1 second to go from here to here. That means the wheel can rotate for 1 second, stop. Rotate for 1 second, stop. Okay, so you put a needle and you have your clock. Right? It's a very simple system. And in the jargon, what they call this an escape mechanism. Whenever the wheel can escape the pendulum, it rotates. And of course, pendulum for 1 second will be as tall as this. So they put smaller pendulums which goes faster and put a lot of gear wheels. So put one more gear wheel, 60 times the second rotates, you have a minute, and so on and so forth. So this was the first thing of Huygens clock. Then what? Huygens did a lot of improvement himself. So what he did was, he did two things. One is, instead of a wheel with a weight, he replaced it with a coil spring. So the coil spring, you wind it and allow it wants to unwind. When it wants to unwind, the wheel will want to rotate, but the pendulum will regulate the rotation of the wheel. Okay, so this is a standard thing for all measurements. As I go on, I'll tell you what replaces pendulum and what replaces the wheel. Huygens also did one more thing. Instead of a regular pendulum, he used a torsion pendulum. It goes this way, right? The torsion pendulum, you'll see a little torsion pendulum here. It has a spring, and it has this whole wheel will go back and forth. Now that immediately released it from being vertical. It doesn't have to be vertical. Now it can be horizontal also because the torsion pendulum works nicely. So from a regular clock, Huygens also made a pocket watch. This came a little later, but he made a pocket watch, and so this is a modern thing, but original stuff is the same. Okay, so now very important was that on Huygens time itself, they could get an accuracy of 1 minute per day. Okay, and somewhere close to much better clocks were developed. So at the end, somewhere around 1700, 1800, we had clocks which had a better time measurement of 10 power minus 4 second accuracy, which was quite remarkable. Now this was why so much of effort went on to measuring time so accurately was actually had something to do with the commerce. By the 1500s, people had started sailing in the all high seas. In the sea, middle of the sea, there is no signpost to say Bombay this way, Cochin this way kind of thing. So there were only two ways in which they identified their location. First is longitude was very easy. Longitude is wait till the night and you look for the pole star. The azimuthal angle of the pole star is pretty much the longitude where you are. Latitude, sorry, that was the latitude. Longitude was a problem. But how they found out with longitude was you take a clock. Let's say you start from Port of Madras, take a clock, synchronize it to Madras Port clock. Okay. Next day, 12 o'clock, you see when the sun comes at the maximum. That is the 12 o'clock wherever you are. Look at the time on the clock which is showing Madras Port time. Okay. So every degree is 4 minutes off. Every degree longitude. Okay. So divide by that. You know, by looking at how much you are off, your 12 o'clock is off by what was the 12 o'clock in Madras. So you know how many minutes you are off. So how much of longitude you have sailed from Madras. Okay. So that, and what now there was a very important problem here. Two problems is that not only the clock has to be accurate, the clock should have very less drift. What I mean by drift is that if 1 second is not exactly 1 second as shown by your clock, let's say it has 0.1 seconds. After 10 such seconds, it's already drifted by 1 second. So 10 seconds have elapsed, but this is showing 9 seconds only or 11 seconds. So when this kind of drift happens, you have errors in your position, and if you have errors in your position, you land up somewhere else. You land up in Timbuktu instead of going to Bombay. So it's a problem, right? And nobody will buy all the goods that you have, or you may end up, you may sail from Cochin with lots of spices, but you come back to Cochin or go to another part of Kerala, who will buy your spices anyway? So, so it's a loss, right? So commercially, it became very important to make better and better clocks. And in fact, in England, there was a prize given of 20,000 pounds, and in those days, it was a huge amount. Even in today, 20,000 pounds is a huge amount of money anyway. So there was a prize, and this guy in 1761 won that prize. And it's a very interesting story. There's a lady called Dava Sobel who wrote this book called Longitude, and she has a very detailed description of how John Harrison made the clock, and he almost lost it. There were some patent issues and all that stuff because of which he almost lost the prize, but finally he did win the prize. Okay. And his clock had an accuracy of 10 power minus 6 seconds, which is quite remarkable, going from 10 power minus 4 to 10 power minus 6. Let's see if this works. It takes a little while to launch. Just give a few seconds. Because I work on the Linux machine, it all has to launch some different programs. You can actually see this is an inverted pendulum. This is the mass switch oscillator. It's a coupled pendulum, double pendulum, and this is the wheel that goes on, and it twice it stops and stops. So this got a much better accuracy than the other thing, any regular pendulum. Okay, this was the grasshopper escapement. It looks like a grasshopper, so it was called grasshopper escapement. That's what this guy won a prize for. Okay, close the grasshopper. So they start logging the RAM. So then there were further better, more and more improvements. There was a guy called Riefler in Germany who made much better coupled pendulum. Most of it were coupled pendulum issues. He went to 10 power minus 7 seconds. You can see each order of magnitude going down was not very easy, right? It may just sound a small number, but making a clock which was very accurate was not that easy going down. And this was probably the best somebody got with a standard pendulum clock of 10 power minus 8 second accuracy, and he used a double pendulum with a master and slave configuration, and they were magnetically coupled. So why again another interesting part of pendulum and accuracy of pendulum is that gravity acceleration due to gravity is not same everywhere. We say 9.8 meters per second, but that's an average, global average. But it goes anywhere from 9.8337 to 9.76 meters per second and 9.825 meters per second. And so not only is G same, and which kind of becomes important if you are trying to launch rockets into space, and even a small difference makes a huge difference in your fuel consumption. And also measurement of G is to an extent what is hidden underneath the earth. So if you have lots of oil or lots of iron, G at that point will have a slight difference. So a better measurement of G, and to this day one of the best measurement of acceleration due to gravity is to use a pendulum. Okay, and there are improvements of pendulum, what's called Cater's pendulum and compound pendulum and all in some of the BSc labs. You keep doing it, and so they are all there. This is kind of a map, roughly telling how T keeps changing across the around 1930s, the quartz clock started becoming important, and quartz clock took over only by 60s and 70s. It became a good commercial success. So what happens in a quartz clock is one takes a very they make a tuning fork out of a quartz thing. Yeah, so that's what this picture is showing. A cut tuning fork, and they are cut in such a way that they oscillate. They have a resonance frequency at 38,768 hertz. Okay, and that is kept in between two capacitor plates and made to oscillate. And you know the whole idea of an LCR circuit. At the resonance, you get maximum oscillation. So the amount of oscillation is also measured capacitively using another capacitor. And what is happening is there's an oscillator which is driving this fellow. And if at any point you see that the quartz crystal is not at resonance, if it goes away at resonance, that means that your oscillator is not oscillating at 32,768 hertz. Okay. And therefore electronics will tweak the oscillator automatically to make it oscillate at 38,768 seconds, 768 hertz. So essentially what we had was a pendulum is now replaced by a little tiny quartz crystal which oscillates, and electronic oscillator replaces that rotating wheel, and the quartz oscillator makes sure that my electronic oscillator is giving me a signal exactly at 32.8 hertz. So why this whole idea of all these funny numbers is this? If I have a regular pendulum, let us say I have a pendulum which takes 1 second to go and come back. Okay. And what is the error you will have in that is 1 second. Okay. The error will be 1 second because you count wrongly, even mechanical counting. If I have a pendulum which does 10 oscillations in a second, then my error, I may miss one or I may add one oscillation extra. So therefore, I would count as either 9 oscillations or 11 oscillations. That's the worst I can do. I cannot go worse than that. I cannot miss 2 oscillations unless I'm not careful. So therefore, when you measure 10 oscillations in a second, your error is 1/10 of a second. Okay. If you have 300 oscillations in a second, then your error is 1 over 300 second. Okay. So that way your error becomes smaller and smaller when you go. So now for a quartz clock, my error is 1 over 32,760. Okay. So that's a very small error, and that's why now all of our watches, everything has quartz clock. And of course, another biggest advantage the quartz clocks made was making it very compact. So I have a quartz crystal oscillator inside your mobile, in the watches, in a pen, inside my laptop, everywhere I have a quartz oscillator. All of them are time. Okay. So, and pendulums are, mechanical clocks are always big. So that made the biggest jump from and we made a huge jump in the accuracy of clocks. Still, quartz clock had a drift of about 10 power minus 8, so not better than some fancy pendulums, but this whole system electronic circuit was much simpler than those very fancy pendulum clocks, which had a much better accuracy, which had an equal accuracy. So that finally brings it in to atomic clock systems, which are the new things. Now what people do is, all these quartz oscillator that we put in our watch is kind of not very highly controlled, but when we need much better accuracy, we have a big temperature controlled quartz oscillator. So that's fairly big because it has to take care of temperature also. And temperature controlled oscillator comes, but this I'll tell you, I'll kind of go back and forth between these two slides. Okay, what is this definition of a second, etc. But just to give a history, atomic clocks came in 1948. That's what I'm going to tell you a little more about it. This is how it looked, the first one. But I'll explain to you what basically this is. This is something you all know, right? This is S and P levels of an atom, and because of LS coupling, we have this. So L is 0 for here, so I don't get 0 minus half, I get only 0 plus half. L is 1, so I get 1 plus half and 1 minus half. 1 plus half and 1 minus half. Then, in some of the alkali atoms, what happens is this L and S couple also to nuclear spin to give me hyperfine levels. Okay, and for cesium, nuclear spin is 7 by 2, and therefore I'll get 7 by 2 minus half, which is 3, and 7 by 2 plus half, which is 4. And this also gets complicated. This is 7 by 2 minus 3 by 2, 7 by up to 7 by 2 plus 3 by 2. So I hope all these levels, but right now we'll not worry about this. We'll look at only these two. Right? These are the two hyperfine levels of cesium, and they are approximately 912631770 hertz, and that has been now accepted as a standard. Okay, so by definition, the definition of a second is related to this one. Okay, and all you have to do now is, instead of a quartz oscillator, I use this is in microwave range. This is 9.1 gigahertz. So I use a microwave oscillator to lock to this transition, and I have an atomic clock. So how does it work is this. I have a cesium oven from which atoms are coming out. The entire system is inside a vacuum chamber. It comes out, and then when I start with this, I have F equal to 3 and F equal to 4. So when atoms are equally divided between these two sublevels, so what we do is, this fellow is a Stern-Gerlach magnet. So F equal to 3, 4 will go that side, F equal to 3 will come here. And here is a microwave resonator, which will, which is exactly getting fed at, what is this? Is a this is called a voltage controlled quartz oscillator. This is a quartz oscillator which is put in a nice temperature controlled oven, and this is giving 9123670 hertz to this guy, and it is fed into this. The atoms absorb that microwave radiation and go from F equal to 3 to F equal to 4. Okay. If it's exactly matching, maximum number of atoms will go. If it's not exactly matching, the number of atoms will be less. So they come out here, and there's one more Stern-Gerlach magnet which will separate out F equal to 3 and F equal to 4. So now F equal to 4 will go to a detector. Usually most of the early clocks use something called a hot wire detector. Every time an atom hits, it will give an electric pulse. So it is seeing what is the rate of atoms that is coming and hitting. So most of the only atoms in F equal to 4 will go. So if I plot as a function of frequency of this, the number of atoms, I'll get something like this. Okay. So whenever this oscillator is exactly at the resonant frequency, I get maximum number. Anytime else, I'll get lesser. This is a Lorentzian graph, it's called. But then Ramsay was doing an experiment for molecular spectroscopy. He did something even better. I'm not sure how much of quantum optics comes in, but anyway, it doesn't matter. So what he does is, instead of using, so we'll look at it like this. The cesium atom is coming here and it's interacting with the microwave over here, and that interaction, so there is a time through which it goes through microwave regime, and so therefore if you stand on the reference point of the atom, it will look like a pulse to me, because atom is moving, the field is not moving at all. So I am going through the field, so field increases and decreases, so it's as good as a pulse. Now depending on the width of the pulse, how much time, the interaction time, the atom will either go from F equal to 3 to
Sorry, I think it's stop sharing the
I tell something?
I don't know. Looks like. Yeah, any and you have 5-10 minutes.
Okay, 10 minutes. I'll be.
I don't know why I can't share.
But I hope we don't share only. So when I went, so I might have pressed on stop share.
Yeah.
But there is a last lot of.
No, but it just happened now.
No, okay.
No, I can still, I can't.
Yeah.
Yeah, now it's good. You didn't know much, don't worry.
Okay, hey. Okay.
It just happened, that's why we told you.
Right. So yeah, so now what Ramsay did was this. So instead of, if I play around with the interaction time, I have ground state and excited state, and if you put the microwave, it goes from ground state to excited state. But if I play around with the interaction time, it kind of comes halfway through, and in that halfway through position, it's actually in a quantum superposition of ground state and excited state. I'll show you a little more probably. Yeah. So it's in a superposition of ground state and excited state, and we have studied quantum mechanics. So we say that ground state by itself is an eigenstate of the atom. Excited state itself is an eigenstate of the atom, but the superposition is not exactly an excited state. So therefore, if I let the atom in the superposition state, after some time it acquires a phase, e power I ht by H cross. Okay, so IET by H cross. So it acquires that extra phase, right? So now what we do is we make it, so we make this into a superposition here. The superposition travels in a field free region for some time. Okay, therefore when it comes here it has acquired an extra phase, and now this second pulse is chosen such a way that it cancels out that extra phase. Okay, so basically what has happened here is because of this length, this is a minus 5 by 2, this is a plus 5 by 2. So that's how we match the phases of these two microwave pulses, and if the phases are exactly matched, then I have maximum transition to go to next excited state. Okay. Now the advantage of this is, and that depends on the frequency here. The advantage of this whole thing is I will get a finer, you saw this, if I didn't have, I had only, if I didn't do that funny business, if I put only one full cycle, this was my resonance curve. When I go there, when I do that funny Ramsey thing, this is my resonance curve. So you see in that big resonance curve, I have finer details here. This is like taking your millimeter scale and writing smaller measurement things over there. So I can, now my measurement accuracy is actually between this and this. Earlier my measurement accuracy was this width, complete this width. Now my measurement accuracy is actually this one. So I get a better measurement accuracy in time measurement with this Ramsey clock. And today it's a commercial thing. There's an institute in Delhi called National Physical Laboratories, who are basically our timekeepers, and they have bought commercial cesium clocks, 5 of them. Okay, they have all kept one over the other. Each one of them is looking at time, and they take an average of 5 clocks, and these clocks go. This is 9.1 gigahertz oscillation. So 1 over that is 1 second. So they convert it into 1 second electrical pulses, and these electrical pulses are fed via satellite. They go to an institute in Germany called Physikalische Technische something. I can never pronounce that big word. We call it as PTB in a town called Braunschweig in Germany. And Braunschweig gets that 1 second pulses from all over the world, from France, from USA, from India, from Africa, everywhere they get, and they keep comparing all these 1 second things. And they take a standard deviation of it. It's called as Allen deviation, and they take the Allen deviation, and if any fellow is drifting, any clock is drifting, they will send back information. If Delhi clock is drifting, they'll send information, your clock is drifting, go and meddle with it. So that is how time standard is set in a universal fashion, and so that is the idea of atomic curve. Okay. To get something better, the basic problem that happens with this clock, still better accuracy can come. I'll just finish in 2 minutes. The problem is this is a thermal oven, right? So the cesium is just strewn out because of heat, and because they are all hot, they are around 50 degrees, or I don't know what is the cesium's vaporization is around 70 degrees Celsius. So therefore, these atoms have a Maxwell-Boltzmann distribution in their velocity. So they are all moving with different speeds, because of which even this gets a slight broadening of that. So what people have done in the past 10 years, this is just to give you an idea of that. It creates into a superposition, and as it comes, it acquires a phase, and then you cancel the phase, you get maximum drift of this, and okay, so we get a 10 power 12. So this is what happens, 10 power minus terms. So we do something called a laser cooling. Now what laser cooling, I'll tell you briefly in 2 lines. Whenever an atom is moving in and it interacts with the laser, it absorbs light and then re-emits it because of spontaneous emission. And in that process, it loses kinetic energy. Atom loses kinetic. Very small, very, very tiny, equal to h cross k, which is like 10 power minus 22. But after several cycles, the atom significantly loses kinetic energy. So what we do is, we have lasers from all 6 sides. Okay, this side, this side, this side, this side, everything. So in all 3 directions, plus x, minus x, plus y, minus y, plus z, minus z, we reduce the velocity of the atoms. And when we reduce the velocity of atoms, what we have done is we have reduced v bar, the average velocity. But average velocity, we know half m v bar square is equal to 3 by 2 kbt. So therefore, if I have reduced v bar, I have as well reduced kbt. Okay, so that is what is cooling. That's why it's called a laser cooling. It's not cooling in the strict sense of there's no heat pump or something like that. So thermodynamics people are a bit unhappy with this whole nomenclature, but we call it laser cooling anyway. So because at least in the Boltzmann temperature, if I look at what we achieve there, we are going to approximately 100 microkelvin, 100 to 150 microkelvin. So this little set of atoms over here in the middle will have a typical temperature of 100 to 150 microkelvins, and then what we do is this. So we have these 6 beams coming here, then we play with this beam for a little while. When we play with this little while, it gives a slight tiny push to the atoms to the top, extra push, because of which atoms get tossed to the top. It's like tossing a ball. And when you toss a ball, it goes all the way up and comes back. Because of gravity, it goes and comes back. And there's a little video which is kind of not the real one. It's kind of made up video. Let's see if it works. It will probably work. Give 2 seconds for it. So what happens is, now I have the microwave cavity. Remember the earlier figure. I have 2 channels of a single microwave cavity. The atoms would go here and then after some time go here. Now I have only 1 microwave cavity. So atoms go, when they go up and then they come down. Okay. Sharing got only single screen, but I'll show at the end of this thing. I'll show you that video. Kind of not sharing. No, it's okay. No, that screen hasn't got shared. Only one screen got shared. Entire screen didn't get shared. But anyway, let me finish this and I'll show that thing. So that what happens is this. So as the atom goes here, it's as if half interaction with microwave cavity. And when it turns around and comes back, it does another microwave cavity. So now there's a laser which sees whether it's in f equal to 3 or f equal to 4. And this microwave cavity is fed by an oscillator which is going at 9.1 gigahertz. If that drifts, then I don't get maximum number of atoms in f equal to 4 will fall down. Therefore, electronics will go around and correct the oscillator, the source that is coming over here. And then you tap that oscillator. I have a 9.1 gigahertz nice source, frequency stabilized to cesium atom, and that's a good thing which will go for all of us. Turned around in my screen sharing. One frozen. Have 2 more slides.
I want you to answer the question.
That's probably that's on your screen. Again, probably it will probably work.
Just take this answer. the slide is
No, no, no. On my screen it says meeting disconnected.
अच्छा, that you rejoin. No, but this is on YouTube. Who's on the on it?
Yeah, it's still showing.
Should I what I stop your sharing. Now you reshare.
No, I've been kind of logged out of that. Not going back in.
But you are here, no, you are here. You are here, you are not logged.
You have to unmute.
No, that is on YouTube. That is no, it's running. Please anyway. Just try reshare.
Yeah, it's taking a little while to go.
Did it disconnect?
No, no, I don't. I think it just.
But you are here, right?
Am I still there? Yeah. Maybe I got disconnected out of. My internet is. I'm signed in.
So why did the net is again? Reshare.
There's no internet.
After that, thing low. Connect to the Wi-Fi.
Ah. Now I see. Somewhere it went to zero.
Okay, now you are connected. Now you should. Same thing as I can see. I really see. Have you all?
Yeah, open.
No.
No, giant computer. Sorry about that. For some weird reason it went off. Okay.
You need that password. Okay. You continue talking.
Okay. So, so that's the basic thing. So what happens in a typical scenario is like there are every country has one standard institution like NPL, Delhi National Physical Laboratory is our timekeeper. In US you have NIST, National Institute of Standards and Technology. Germany the PTB Brunswick is the guys, and France there's a French observatory. They are the people. So all of them have a set of cesium clocks, the thermal oven cesium clocks, which are continuously running, and they also have a laser cooled atomic clock in another room or in the same room. Periodically, they look at the standards of between the laser cooled atomic clock. What we call it atomic fountain because atoms go up like that and come down. And atomic clock and cesium clock are compared a little bit. So Delhi guys also about for the past 10 years they started working on building an atomic clock, for fountain clock because that's not easily available. You have to build it post disabled.
Now it is. Now it is. Now it is.
Okay, so India has now an atomic clock running, although it's not completely, what would I say, stabilized and functional. Uh, might have a that. So this is just a schematic of it. This is not the real stuff. So it's showing you laser cooling happens. It takes a few hundred milliseconds to get all the cold atoms. Then the cold atoms are tossed, and then they come back in the same microwave, and they're detected on a. So that's the toss goes up, and they come back. Falls because of gravity, and that's how. That's how a standard laser cooling clock works. And so this every country has its set of laser cooling. This is the one. Physikalisch, technische, Anderson, Stout, Brunswick. That's where they do it. And so every country you can see all the Japan, NIST, etc. There should be a picture of yeah. This is the atomic clock in NPL Delhi. This is where these are basically there is a mu metal shielding around the tossing experiment. So inside it is what I showed you, the tossing thing, and all the lasers and the control electronics that needs to be done is on this table. It's on a separate table, all closed nicely kind of.
How often do they need to be set?
It's supposed to run continuously. Right now, every 15 minutes they have to keep meddling with it.
15?
Yeah, this is this one. So they're building another set where they need to meddle it much less. They're improving their design on this one. So that atomic clock may take another 2 years before it becomes really functional. And this is actually one of their first Ramsey signals from that system. So yeah, that just to give you an idea how we are going from Huygens to 10 power minus 4, we are reaching 10 power minus 12, minus 15, we are going up to minus 16 now. And just one little thing as to why so much of accuracy is all needed is this. Your GPS, all your GPS works in this way. So you have your phone sends a signal to 3 cell towers, and each of the cell tower finds out at what time the signal came in. And if you are exactly in the middle of the triangle, all the 3 cell towers get your signal at the same time, the ping. Okay. If you are closer to one of the towers, that tower gets a faster ping. Right. So using this method, which is called as triangulation, you can very accurately point your position. Now extend the cell towers to your GPS satellites, 3 geostationary satellites. So you can essentially mark your position to a high accuracy. If I want 1 meter accuracy, I need these 3 clocks should be synchronized, and they share the timing up to 10 power minus 16 second precision.
For 1 meter.
For 1 meter.
That doesn't you don't have that.
15.
We are less than 1.
We are less than 1. So usually it's a 3 meter accuracy is what all GPS gives you. So the
How far are the towers?
these towers are kind of speculative. Closest.
Closest 3 towers.
Closest. There's no specific. It should form a triangle. That's all.
And the nearest.
Nearest 3. So basically, the equation involves your arm length and the position. Okay. So we'll not worry about this. This is an atomic beam thing which is going on, which will probably bring in the help of DRDO, which probably works by next year or the year after that. So I forgot to put that. So that's the thank you slide. So, any questions in this thing?
Any questions?
Yeah, yeah.
See, they do this in BSc. There are some
Flywheel experiment. Torsion pendulum, yeah. So all of them, you know where they go finally. That becomes your clock. You open up some of those old clocks if you have, especially those. If you have a watch that it's got a little beautiful spring, and then you just tip it, and then it will start doing oscillations. Fine spring. I also don't have, but we should take those things to the lab and show them when we show torsion pendulum. See where the torsion pendulum becomes really application. Show those old watches.
I do have a question. How do we synchronize on So how
it is not exactly synchronized at this point, but what it does is if there is a drift in any one of them. So these electronics, the microwave oscillator which is feeding the microwave, that's all the control I have. So I fiddle with that, and I can change the amplitude, the frequency, and the phase. All the three I can. So when you are talking of synchronization, I basically play with the phase. I play with the phase so that your things go back and forth. So there I'm making it synchronized to the rest of the process.
just like suppose if you are played by
Nano, yeah.
Like that.
So I can twiddle it to that accuracy. It's an extremely
Like message using let them on
no message. Okay, the message will tell you how far away you are from standard deviation, right? From the normal, your standard deviation it will tell you. So based on that, I have to recalculate how far I am and how much I have to adjust.
like a problem.
It is like that. It's like that.
Thank you. So I would like to thank you, sir, for such a lovely lecture on time, especially in cyberspace like Hyderabad, where hardly people take take care of time. So it was such a wonderful and nice talk. I once again we found the faculty and everyone we welcome you and thank you for such a lovely talk. Thank you.
Now, as a token of gratitude, I request Dr. Priya to be the next state Ashok.
And then
So, since we are already late, we'll start with the technical session. The session will go as per schedule. So, I hope you are ready with your slides. So, Dr. Priya will calling your name. We have just 8 to 9 minutes. Stick to the time because already we are late. So, we'll call the first speaker.
So let's start with the first one, which is Shanmuki Joshi. Jyoti. Sorry. Shanmuki Joshi. I hope you are logged in. Yeah. Oh, sorry. I made a mistake. The first talk will be by Ismail Ahmed. Ismail Ahmed, are you there?
Yeah, good afternoon, ma'am.
Is Ismail Ahmed there?
You can unmute.
I don't see him. So who's this one? Yeah, okay. So Ismail Ahmed, now you can share your screen.
Okay, thank you, ma'am. Am I audible to you, ma'am? Am I audible to you?
Please, go on to slideshare mode. Ismail? Turn your camera also if you want. Yeah. Okay.
Thank you, madam. Good afternoon, participants. I'm very thankful to the management of Manu and Physics Department for giving me this opportunity. Myself, Dr. Syed Ismail Ahmed. I'm working for Ibn Sina National College here in Jeddah. Today, my topic of presentation is rare earth, cerium, samarium, and gadolinium substituted spinel ferrites. Herein, I will discuss structural, magnetic, and dielectric properties.
Sir, please go to slide share mode. No? Press F5.
Slide share. Okay. One moment, please.
Yes.
F5, sir. Is it okay, ma'am?
Yes, perfect. You can start.
Yeah, thank you. The outline of the presentation today is I will be giving introduction of the ferrites, then metal substituted spinel ferrites, and synthesis of this rare earth cerium samarium substituted cobalt ferrite, and characterization by XRD, EDAX, and FTIR, then magnetic studies at room temperature and also at low temperatures, then dielectrics, finally conclusion and results and references. So the picture you see on the right is a spinel ferrite, which is FCC type. Ferrites, the magnetic oxides, they are broadly classified. The topic of discussion ours today, spinel ferrite. This is based on the crystal structure, where hexaferrites are A equal to B, but not equal to C, where you have stack of a layer of atoms on C axis, whereas orthoferrites are basically, they are perovskites, distorted perovskites like barium titanate, and garnets are orthorhombic, and the spinel ferrites are cubic in nature. They are again classified into normal ferrites, mixed ferrites, and inverse spinels that I will show in the next slide. And furthermore, based on the magnetization, how they can easily magnetize and demagnetize. Okay, by hysteresis curve, we can classify them into hard and soft ferrites. And the hard and soft ferrites. Hard ferrites are one which requires a lot of magnetization, applied magnetic field in reverse direction to make the magnetization zero, whereas soft ferrites are easily magnetized and demagnetized. This is the crystal structure of spinel ferrites. I will be concentrating on spinel ferrites. 1 octant of the structure is shown here. Yeah, this is the unit cell where you have two sublattices A and B. The A sublattice is tetrahedral and the B one is octahedral, where the cations are surrounded by oxygen ions. Okay. This is the octahedral and tetrahedral sites, and octahedral sites. And these ferrites are general formula Ab2O4, where A is the divalent metal ion, usually the transition metal, whereas B is the ferrous Fe2,3 plus and chalcogenate oxygen. As I said, these ferrites can be classified into spinels, mixed ferrites, and inverse spinels. So their general formula can be written as the divalent metal ion, as I said, A. Okay, at A site, this one, the A site atoms and B site atoms. So this is delta is the degree of inversion. If delta equal to 0, this is perfect spinel. If delta is equals to 1, it is inverse spinel. Inverse spinel means this will become 0 when delta equal to 1. So the B side atoms are equally shared on A and B side. Yani ferrous atoms are equally shared on A side and B side. This is the inverse spinel. In many cases, the spinal ferrites are mixed one, where delta will have values between 0 and 1. These are some of the applications of ferrites. This is the cobalt ferrite doped with zinc substituted cobalt ferrite. Some of the applications are they are used highly in photocatalytic activities, wastewater treatment, dye removal, and antibacterial activities. Also in drug delivery and magnetic hyperthermia. So likewise, we have chromium substituted ferrite and gadolinium substituted ferrite. Magnesium, soft magnetic materials, magnesium substituted ferrite. If you see the formula over here, say zinc, the substituted zinc one is occupying A side, replacing the cobalt atoms at A side. And likewise, if you see the gadolinium, the R says gadolinium, this will occupy the B side, replacing the ferrous atoms at the B side. This is the crystal structure. Likewise, nickel ferrite, it is a perfect inverse spinel structure. We have synthesized cobalt substituted samarium cerium. Samarium cerium substituted cobalt ferrite with the general formula COFe2 minus X minus Y, X MX, CEY. And they are the X and Y are the concentrations of the substituents O4. The sol gel autocombustion method has been utilized to synthesize this. Metal nitrates of ferrous, cobalt, and samarium metal of metals in the stoichiometric ratio is taken and is dissolved in the deionized water, distilled water in the stoichiometric ratio. And citric acid has been used in 1:3 ratio. This citric acid has been used as a chelating agent as well. This works as both fuel and chelating agent. And then the solution was heated up with the hot plate with continuous stirring and heating by adding ammonia to keep the solution pH 7 buffer. So at 200 degrees centigrade, a viscous gel has been formed. Further heating, at all of a sudden, a fraction of seconds, this gel has ignited, and a combustion process has occurred, giving large amount of gases, wherein a fluffy gray substance has been obtained as a precursor powder. This powder is further annealed at 500 degrees centigrade for more crystallinity, and the further has been furthermore the powder has taken and pelletized by pressing with the pelletizer by adding polyvinyl alcohol as a binder, and after binding this, after pelletizing this, the pellets have been sintered at 350 degrees centigrade and further sent for the characterization. The characterization we have, this is the equation that involved in the process. The nitrates of cobalt, ferrous, FeNO3 nonahydrate, and likewise samarium hexahydrate, and cerium and citric acid. The process after combustion, large amount of gases, nitrogen, carbon dioxide, and oxygen has been evolved. Further, we have characterization. We have characterized this XRD for X-ray diffraction for lattice parameters, particle size, and X-ray density. Also, we have drawn Williams and Hall plot using this data and scanning electron microscopy to find the surface morphology and to confirm the presence of all the elements in the stoichiometric ratio. We have used elemental analysis by EDAX and FTIR technique we have used to confirm the spinal structure and also to find the place of the cations we have substituted the dopants. And vibrating sample magnetometry at room temperature and at also low temperature. An LCR meter has been used for the dielectric measurements.
So sorry, you have 2 minutes more. Yeah.
Oh. Okay. Okay, I will move fast bit. We have discussion we have here the XRD. Okay, they have observed a shift in the character is the lattice parameter has been increased and then decreased. And the X-ray density goes on increase due to the peak weight. The crystallite size, okay, decrease due to the substitution of rare earth metals. And if this is the Williamson plot, okay, the slope is shown here. So these are the equations we have used to find the Shear's equation to find the crystallite size, and strain has been obtained by the slope of this curve. And this is the specific surface area. This is the surface morphology of the synthesis sample. We have predicted the distribution of cations on both A and B sites. We have taken delta as 0.2. So cobalt, this is the A site atoms, this is the B site atoms. And further substitution of the rare earth ions, that they occupy the B site atoms, B site, the octahedral site in the system. And this is the lattice parameter theoretically observed. This one is the FTIR spectra. These are the two characteristic peaks, nu1 and nu2, given octahedral and tetrahedral positions. These are the results. What we have observed, the striking, the point here is the force constant which have been calculated using this formula, where m is the reduced mass. The force constant is goes on increase with the content, the rare earth substituted cerium and samarium. This shows that the substituted atoms occupy the B sites. And this one is the hysteresis curve. It can be observed that the magnetization goes on decrease with the concentration of the rare earth metals. Further, we have the hysteresis. Hysteresis also decreased, and the further characteristics we have. This is one, the YK angle. YK angle has been increased here. Coming on to the low temperature, we have two mechanisms to characterize it: zero field cool characterization and field cool. In the zero field cool,
sir, please provide your conclusions.
We have, okay, sure. To conclude this, we have synthesized this material using the sol gel auto combustion method. Internal strain has been found in the samples, and the magnetization decreased with the Re substitution because of the weakening of AB interaction. We have three types of interaction: AB, AA, and BB interaction. AB interaction will dominate the other two. So AB interaction has been decreased. That is what the magnetization has been decreased in the sample. And the YK angle. The YK angle has been increased due to the surface morphology and the defected samples. This is the acknowledgement, and these are the references which we have used. Thank you very much.
Yes, thank you, Dr. Rahman. Any questions? Please.
Yes, please. Yes, I'm audible. Yes. Yeah. Please go ahead. Please go ahead. Yes, please go ahead, please.
APR, SCIR, APR.
Yes.
Is it APR? So please,
Ma'am, you are not clearly audible, please.
the question is, have you used APR? FTR.
FTIR, okay.
Have you used FTR or ATR?
No, FTIR only. The plate base. Yes. Not attenuated total reflection. No, FTIR only.
Okay. Thank you, sir. Thank you so much.
Thank you very much. Thank
So
you.
we move on to Dr. Shanmukhi Joshi. Yeah, please share the screen. Please share your screen. And we can't hear you. Yeah. Shanmukhi Joshi, please share the screen. Please not. We can't hear your voice. Hello, madam, we cannot hear your voice. Please unmute yourself and please can't hear you. Ma'am, we cannot hear your voice. Now unmute. Please talk. Unmute yourself. Please unmute yourself and speak. Yeah. We can't hear your voice.
Hello.
Hello, please. Please unmute yourself.
Is it okay, ma'am?
Yeah, now it's good. Good.
Is it okay, ma'am?
Yes. So you can start.
Yes, ma'am. I'm Dr. Shanmukhi Jyoti. I'm from Government Degree College for Women, Hussaini Alam, Hyderabad, ma'am. And I'm here to present the optical properties of copper doped V2O5 nano powders, ma'am. Actually, our work we have started for promotion of gas sensors. So we have started the work and we have come up to half of the work, ma'am. So what all I could complete the work, I'm presenting it now, ma'am. So my, 1 second, ma'am, somehow my PPT is not moving away. 1 second, ma'am. My PPT is not moving. Yeah. My work goes with as introduction, my description of my work and results and discussions and summary and conclusion. So my motivation of the work is that volatile organic compounds are considered as significant contributors for indoor air pollution, ma'am. Short and long-term effects on human health are there because of the nature ecosystem. According to the World Health Organization, lung and stomach cancer is one of the leading causes of death. So VOCs are often suitable for as breath biomarkers. So biomarkers, any substance, structure or process that can be measured in the body or its products and influences or predicts the incidence of outcoming of disease. So there are different types of sensors: optical sensor, calorimetric sensors, mass sensitive sensors, electrochemical or solid state sensors, or conductometric sensors. And I'm going to concentrate only on the conductometric sensors, which are of solid state type. So chemical sensors have played an important role in industrial, medical and domestic applications in detecting pollutant and combustible gases. Among chemical sensors, metal oxide semiconductors play an important role in processes, from some of which are ZNO, SNO2, WO3, IN2O3, V2O5 and TiO2, which are widely studied metal oxide gas sensors. for gas sensing application. Further research is under progress to increase the efficiency of a gas sensor. So several approaches such as surface modification by nanostructures, catalyst functionalization, elemental doping, and heterostructure formation have been developed to enhance the performance of sensors. So in these approaches, elemental doping has received most attention due to the hybrid properties, which can give more versatile combinations. So here we have selected vanadium pentoxide, which is of great attention. In this, we have doped the vanadium pentoxide with copper. Later on, we characterize for different techniques. So I have taken the vanadium pentoxide, pure vanadium pentoxide powder from Sigma Aldrich, and copper metal powder from Thermo Fisher Company. And I have utilized the powders. I have prepared the powders, doped the powders for, we have grinded the powders for at least 48 hours. And we have taken the copper doping concentration as 3 atomic percent and 5 atomic percent. Therefore, and thereon we studied for structural, morphological, optical analysis of the films, which are to be carried out for XRD, SEM, optical, IDAX, electrical, and gas sensing to improve the sensitivity and response by time by adding the dopant. These are the different ways how the characterization techniques can be done. So sample particle size, we can do it by XRD and LDS, and surface also. Sample surface composition, we do it by XPS, and later on optical parameters by UV visible spectrophotometer. So to prepare the powders of vanadium pentoxide by physical method and by annealing at different temperatures, we have done the annealing, and we have confined ourselves to the annealing at 500 and 600 degrees centigrade. But here I am providing only 600 degrees centigrade annealing temperature readings itself. So the required properties of these nanopowders to be used are in many applications can be tailored by varying the grain size, which can be achieved by varying the annealing temperature, which is the best process to vary the grain size. So this is what is about the chemical composition of V2O5, its molecular weight, its appearance, its melting point is 690, its boiling point is 1750, density is 3.35 grams per centimeter cube, exact mass is... Yes, sir? These are the general properties of copper. These are my samples which we have taken, and out of which we have...
Hello, I'm sorry, please mute yourself.
What, ma'am?
Yeah, continue.
This is my flow chart. We have taken pure V2O5 powder and pure metal copper metal powder, grinded 48 hours, and we have annealed at 600 degrees. Later on, we have done the characteristics of XRD, structural, morphological, optical, and electrical characterizations. So these are the XRD parameters which I have taken, and we could see that 001 is the highest peak in these, wherein we can see that the copper elemental doping has been perfectly, the copper has been absorbed by purely V2O5. So we can see the peaks at 24.3 degrees, 25.3, 31.4, 35.8, and all these are in confinement with, are in agreement with the JCPDS card number of 892482. Therefore, these show that they are highly polycrystalline and which have an orthorhombic phase with a preferred orientation of 001. So these are the crystallite size which have calculated with the Debye-Scherrer methods, and pure V2O5 with the crystallite size was 74. For copper 3 atomic doping, we have 38, and 5 atomic percent, we have 22. These are the SEM images of all the 3 samples, and the grain boundaries become more distinguishable after annealing at 600 degrees and become very indistinct owing to the growth of grains after heat treatment. This indicates the structure formation from complete amorphous to crystalline size takes place. So these are the absorbance curves. So the absorbance curves was found to increase with increased doping concentrations. These are the transmission curves, transmission spectra curves. And this is the energy band gap. So the energy band gap, we can see that as the concentration of copper increases, we can see that the energy band gap is decreasing. So the increase in band gap values from pure to copper V2O5 powders is attributed to the increased carrier concentration. So the result, the energy gap results show that the energy gap decreases with increasing concentration. The addition of copper assimilates into which causes a shift towards the longer wavelength owing to the reduced band gap. So the decrease in the band gap for copper doped V2O5 films is due to the doping of copper, which creates impurity levels below the conduction band of V2O5. Such an optical band gap reduction was also noticed in tungsten doped V2O5. This I have given in the reference also, madam. Donor level is created to narrow the band gap, and this owes to doping of copper ions, leading to reduction in energy band gap. And these are the electrical properties which we have done. The all parameter have been done in our lab in Government Degree College, Hussaini Alam, and optical parameters also. The instrument is available in Government Degree College, Hussaini Alam, madam. We have done the readings here itself. And it is evident from these figures that the conductivity rises as a result of creation of oxygen vacancies, which is what is referred to as low mobility in N-type semiconductors. Doping has a significant impact on the material's mobility overall. So for 3 atomic and 5 atomic of the doping, the resistivity and the mobility of the film decrease, while the conductivity values are inversely proportional to the resistivity values. So based on these readings, we can conclude that based on current advances in the field of metal oxide gas sensors, so we can go for gas sensing by controlling the morphology and structure of sensing materials, which is one step ahead. So the size impact as well as the porous nanostructure that could allow the ultra-sensitive detection, novel nanostructures and nanocomposite that could allow ultra-sensitive detection also, applying a chromatography approach to porous nanostructures with quick reactions and recovery properties, increasing doping concentration and adding new dopants may allow the development of new sensing materials. These are my references, madam, and thank you, madam.
Thank you very much. Do we have time for one last question? Thank you so much, ma'am.
Okay, ma'am. Thank you.
We'll move on to our next speaker. Our next speaker is Dr. Madhu Dharmapuri. Please stop your share. Yeah. Ma'am, you can share. Madhu Dharmapuri, you can share your screen. Hello, are you there? Madhu Dharmapuri, are you there? You are there, logged in, right?
Yes, madam. Yes, I am sharing.
So please share. Please share your screen and you start your presentation. Yeah, please go on slideshare mode.
Is it visible, ma'am?
Yes, it's visible. Please go on slideshare mode.
Okay. Is it okay, ma'am?
Yes, perfect. You can start.
Good afternoon, everyone. Myself, Madhu Dharmapuri, research scholar, working under the supervision of Dr. G. Upender, Associate Professor of Physics, Usmania University, Department of Physics. And the title of my talk today is Synthesis of CD2SNO4, CuBi2O4 Z-scheme heterojunction as efficient visible light photocatalyst for dye degradation. And outline of my talk is introduction, objectives, materials and methods, results and discussion, conclusions and acknowledgements, and why we need photocatalysts. The world has been facing the biggest problem these days, particularly environmental pollution, water pollution. To address these kind of global issues, photocatalysts are mainly used to address these issues. And what is photocatalyst and what is photocatalysis? Any catalyst, the aim of any catalyst, the function of any catalyst is to enhance the rate of chemical reaction without being involved or without altering the byproducts. And if that function is happening under the presence of light, then we call it as a photocatalyst. And the phenomenon is known as photocatalysis. And for any photocatalyst, so there are certain conditions to be satisfied by it so that it can be efficiently used for its purpose. And it has to have a band gap in the region of visible light and low charge recombination rate and chemical stability, thermal stability, non-toxicity, and last but not least, we have to be able to manufacture it or prepare it at low cost. And this is the schematic diagram of photocatalysis, where a light is falling on photocatalyst, and as a result, electrons are excited into the conduction band. And if we can stop the recombination, and the excited electrons will react with the atmospheric oxygen, so that they produce superoxide radical. Similarly, holes in the valence band will react with the atmospheric moisture, so that they produce hydroxyl radical, and these superoxide radical and hydroxyl radical in turn will react with the degradants like methylene blue, and will give you byproducts like carbon dioxide and water. And these are the some of the reactions involved in the photocatalysis process. And in photocatalysis, to increase the efficiency of any photocatalyst, there are some certain things to be done, like controlling morphology and doping with transition metals, and making heterojunction or composite structures, which enhances the photocatalytic activity. And in our work, we have taken up the making heterojunction structures, where particularly type 2 heterojunction structures were prepared. That is direct jet scheme heterojunction, where the electrons from the semiconductor 1, conduction band of semiconductor 1, goes to the valence band of the semiconductor 2. As a result, we can successfully stop the recombination of these excited electrons when the light falls on it, so that the excited electrons can form superoxide radicals, and the holes left in the valence band can form hydroxyl radicals. They in turn will react with the methylene blue we have chosen as a model organic pollutant here, that is being degraded into carbon dioxide and water. And in this work, we have prepared CD2SNO4 and CuBi2O4 using hydrothermal method, and we have prepared the composites and characterized with XRD, SEM, EDX spectra, and UVDRS. And scavenger tests were also performed to confirm whether what kind of active species are there to form these radicals. So hydrothermal method is a most environmental friendly one-step synthetic procedure, where we use low temperatures. Particularly, I will explain the synthesis very clearly in the next slide. And the reason we have chosen these two compounds are their band gaps are in the region of visible region. And this is the schematic diagram of a synthesis, where we have used cadmium acetate and tin chloride pentahydrate as the precursors, and they were mixed in a 25 ml of doubly deionized water, and then one is mixed into another dropwise and stirred on the magnetic stirrer for 30 minutes. Then a pH is adjusted by adding NaOH, and that
ఎందుకు అది మిల్లెట్స్ మీద
then it is the solution is transferred to autoclave, which is placed in hot air oven for 12 hours at 180 degrees centigrade. Then after allowing it to cool down to the room temperature, it was washed 3 times with doubly deionized water along with ethanol, and dried at 80 degrees centigrade, and grinded it to a powder, which is now a CD2SNO4. And the same procedure is used for CuBi2O4 synthesis. In the place of cadmium acetate, we used copper nitrate, and in place of tin chloride pentahydrate, we used bismuth nitrate, and everything else is same. And this is the XRD pattern of all the composites along with the parent compounds, and the phase of each compound is confirmed, and they were in agreement with the JCPDS data. And these are the FECM images of the composite particularly I am giving the data of the best composite. We have prepared actually 0.9 CSO, 0.1 CBO, 0.8 CSO, 0.2 CBO, and 0.7 CSO, 0.3 CBO. Out of these three, we have got a best photocatalytic activity for 0.8 CSO and 0.2 CBO. And this is the efficient image of that particular sample, where we can see CBO microstructure as well as CSO microstructure present in this particular efficient image, where cubes are representing CD2SNO4, whereas these cauliflower-like shapes are belonging to the CuBa2O4. And EDAX spectra has been taken, in which the atomic weight percentage of all the elements present in the composite was in agreement with the stoichiometric ratio of all the elements, and there were no impurities present. It was confirmed from this EDAX spectra. And we have also taken the UV absorption spectra, UV-DRS spectra, from which we have calculated the band gap of each semiconductor and each composite by using this equation. And in our work, the CD2SNO4 is a N-type semiconductor, and CuBa2O4 is a P-type semiconductor. And here in this equation, N is equal to 1 for direct band gap and N is equal to 4 for indirect one. And in our work, the both compounds are direct band gap semiconductors. And this is a tout plot of the best composite along with the parent compound, the right side one. The left side one is the UV-DRS spectra of all the compound that we have prepared. And this is the absorption spectra. Actually, we have performed photocatalytic activity under the presence of visible light for 3 ma'am. Madam?
Please conclude soon.
Okay, ma'am. And we have calculated the degradation percentages with the UV absorption data taken from the photocatalytic activity results, where this is the formula, the concentration of the MB with respect to time in the dark. CO is the dark concentration and CT is the concentration of MB at a particular time. And we have got 60%, 66%, 80%, 97%, and 81% are the degradation percentages of the samples have shown here. Out of all the samples, including parent samples, we have got the best photocatalytic activity percentage for 0.8 CSO and 0.2 CSO, or 0.2 CBO. And this is the photocatalytic activity, the photo degradation percentage of all the samples. And we have also calculated the band edge potentials of each compound and each composite, and they are found to be like this. And this is the schematic diagram of Z scheme, the right side picture, where it is the electrons are transferring from valence conduction band of CuBa2O4 to valence band of CD2SNO4, so that the electron hole recombination has been reduced. And scavenger tests were performed. Benzoquinone, ammonium oxalate, and terbutanol were chosen as scavengers to confirm whether which type of active species is involved in these reactions. And we have found that the benzoquinone was suppressed much more than the other scavengers, which confirms that superoxide radical is more active in MB degradation, along with the holes also. And conclusions. And we have successfully prepared a novel heterojunction photocatalyst, which was successfully degraded MB dye. And the Z scheme mechanism was particularly explained in this work. And superoxide radical was playing significant role along with the holes. Thank you.
Thank you very much. We'll now move on to our next speaker, Riaz. I'm sorry,
Hello, ma'am.
Start sharing.
My slides are visible?
No, go on slideshow mode.
Okay, ma'am. Thank you. Good evening. My name is Riaz, and I am a research scholar from Department of Physics, Aligarh Muslim University. And the topic of my presentation is structural and microresorbent properties of neodymium to barium hexaferrite. This is the outline of my presentation.
You can start your
As a result of the advanced, hello,
Yeah, you can start your camera.
am I audible?
Yes, you're audible.
Okay. Okay. Is it okay now?
Yeah.
Okay. So as a result of the advancement of the electronic devices, the amount of the electromagnetic radiation is increasing exponentially. That's why this unwanted electromagnetic radiation affect the performances of the other electronic devices present nearby. That's why we need to develop such kind of material that have capabilities of absorbing this material and that can be used as a shield against this radiation. That's why EMI shielding basically is a process of reducing the effect of unwanted electromagnetic radiation to affect the performances of the electronic devices. So here in this slide, I have shown some basic sources of the electromagnetic radiation that we are surrounded by, and this figure shows the microwave spectrum. So basically, EMI shielding was first discovered in about 1940s after the first nuclear detonation. And it was observed that the semiconductor device that was used to monitor the effect of the blast was destroyed due to the intense electromagnetic pulses. And due to electromagnetic interference, many consequences happened. Like here, I have shown in this pictures. The first picture shows the car crash because due to the EMI interference, the signal in the car, that is automatic braking system, stopped working and they collide. Similarly, due to the mismatch in the aircraft, the unwanted deployment of the bombs and crash happened in the history. The electromagnetic interference shielding is used in all the electronic devices ranging from consumer electronic to medical devices that I have shown here in this slide. So for shielding material, I have choose barium hexaferrite. There is a variety of the material that are used for such purposes, but I have used barium hexaferrite because it has good magnetic properties that are governed by Fe3 plus ion distribution at the tetrahedral and octahedral side of the structure of this material. It has very high Curie temperature and high electrical resistivity and magnetic anisotropy, which is the requirement for a material to be good lossy. And it is suitable for the application of high frequency also because of high saturation magnetization and coercive field values. These are the synthesis process. We have optimized the solid auto combustion method to synthesize our sample, and these are the steps. We have taken ferric and nitrate precursors in the proper stoichiometric ratios in distilled water, and then we have used citric acid as combustion agent, and to maintain the pH of the solution at 9, we use ammonium hydroxide. These are the different processes. The first process in which the viscous gel was found after 1 hour, and then this gel was dried for 1.5 hours, and finally it was grinded and calcined at 1050 degrees centigrade for 5 hours to obtain final BHF nanoparticles. To confirm the X phase formation, we have done the XRD of our sample, and all the peaks are in agreement with the standard data. And to understand the nature of the stain and crystallite size of our sample, we have also plotted the Williamson-Hall plot of our sample. And for finding the other necessary parameters like volume, lattice volume, and density, we have also done the relativity refinement, and these parameters are given in the slide. And here in this slide, I have shown the we can see that is modifying the structural conformation. We have done the Raman spectroscopy. In our sample, 1 unit cell of barium hexaferrite contains 64 atoms, which give rise to 189 optical modes, out of which 42 are Raman active and 30 are Raman inactive. 30 are IR active. Vibration mode present at 520 centimeter inverse and 611 centimeter inverse correspond to stretching of iron and oxygen band in octahedral side, while the band at 170 centimeter inverse correspond to the stretching of hydrogen and oxygen band in tetrahedral side. The vibration mode present at 520 centimeter inverse correspond to stretching of in M-type barium hexaferrite positions in our. Moreover, we have also recorded the FTR spectra in the frequency range from 400 centimeter inverse to 4000 centimeter inverse to have more information of the internal structure of the material. and the absorption band present at 590 centimeter inverse and 438 centimeter inverse correspond to iron oxygen vibration at tetrahedral and octahedral, which confirm the presence of tetrahedral and octahedral site in our sample. We have also calculated some other parameter like force constant, and that I have shown here in this table. To investigate the morphology, we have recorded the SEM micrographs. This picture shows the SEM micrograph of the material of the pristine and 20% dope sample along with their EDEX spectra. The SEM micrograph show the uniform morphology of the sample, and while EDEX confirm the elemental composition of the samples. To understand the different concentration of the elements, we have also recorded the X-ray photoelectron spectra of our sample. This is the first full survey spectra of the pristine and 20% dope sample, which shows all the elements and different oxidation state of the element present in this. For finding the concentration of the different elements, we have also recorded the these are the high resolution spectra, XPS spectra. Here the separation. Here we can see the splitting of the levels. Like barium is split into doublet and iron is split into doublet, which confirm the different oxidation states of the iron and barium in our sample. These are the high resolution spectra for the dope sample. To understand the magnetic property, we have recorded the image loop of our sample at room temperature from plus 18 kilo state to minus 18 kilo state, and the maximum magnetization was achieved 44.3 EMU per gram for 5% dope sample, while its value reduces for further dropping to 39.6 EMU per gram for 20% dope sample. The increase in saturation magnetization might be due to the particle size effect, as the particle size increase after doping. We have also fitted this data to extract different parameters like saturation magnetization and corrosive field that I have shown here. We can see that after doping, the saturation magnetization value is decreasing. After doing this, we have fabricated the composite of this material in epoxy resin with 8% weight. These are the results of the vector network analyzer, which shows the complex permittivity and permeability and dielectric and magnetic loss tangents. We can see that after doping, the loss tangent is increasing, so that we can say that after doping, the loss in our material is increasing. That is our requirement. Using this data, we have calculated the reflection loss, and we have found that our sample has 10% dope sample has maximum reflection loss of minus 13 dB at the frequency of 10.5 GHz, which means this sample is suitable to absorb 95% of the incident radiation in this frequency region. And we have also calculated the refractive index of the 10% dope sample using the dispersion relation shown here. And the drop in refractive index generally occurs over. Okay, ma'am, just one slide is left. It's called anomalous dispersion or resonant dispersion. These are the conclusion. So we can say that we have successfully synthesized barium hexaferrite, and we have found that the 10% dope sample has maximum reflection loss, and its value is it is very capable of absorbing 95 to 99% of the incident radiation on the surface of the material. Thank you.
Thank you, Riaz. Thank you. Sorry,
Okay.
we are out of time, so we need to. Yeah. Thank you so much. Is there a fast question? Okay, so we move on to the next speaker. Thank you, Riaz. So we move to the next speaker, Sharika Afid. Sharika, please share your.
Yes, ma'am. Hello. Hello.
Yeah, we can hear you.
Am I audible, ma'am?
Yes.
Ma'am, actually, I'm presenting here. So, ma'am, can you? I'm not able to share the screen.
Please share your presentation. Yeah, you can share gel. So Sharika, please
No.
share your presentation and start.
Okay. Yes, ma'am. Good evening, everyone. I am Sharika Afreen, working as a research scholar in the Department of Physics, Aligarh Muslim University, Aligarh. The topic of my presentation is effect of synthesis methods on the structural and morphological properties of cobalt oxide nanoparticles. So this is the outline of my presentation. First, I will discuss the motivation, and after that I will discuss the synthesis process that I have used to synthesize the cobalt oxide nanoparticles. After that, I will discuss the results, and finally I will conclude. So the properties of nanocrystalline materials can be tuned by varying their size, geometry, and morphology depending on the application area. The choice of an appropriate synthesis method for nanoparticles with desirable property is a crucial factor. So the synthesis of cobalt oxide stands as an important area for research with far-reaching implications for numerous applications, including catalysis, energy storage, and sensing technologies. And the choice of synthesis method plays a critical role in determining the structural, morphological, and functional properties of the resulting material. So there are various synthesis processes that are used to synthesize the nanoparticles, but I have used here Solvay autocombustion and co-precipitation methods. They have emerged as promising routes for the synthesis of cobalt oxide and any other nanoparticles due to their versatility and tunability. However, a detailed comparative analysis of these methods is essential to identify their respective advantages, limitations, and impact on the final product. So cobalt oxide belongs to the normal spinel crystal structure, and it is a p-type semiconductor with special interest due to its potential applications as sensors, heterogeneous catalysis, electrochemical devices, lithium-ion batteries. So this figure shows the crystal structure of cobalt oxide, in which cobalt 2 positive ion occupy the tetrahedral sites while cobalt 3 positive ions occupy the octahedral sites. So here I have shown the figure of tetrahedral coordination and octahedral coordination geometry. So I have used Solvay autocombustion method to synthesize the cobalt oxide nanoparticles. In this synthesis process, I have taken cobalt nitrate solution in distilled water and a citric acid solution in distilled water. After that, I have added the citric acid solution into the cobalt nitrate solution while continuous striding at 860 degrees centigrade. And after that, I have added the ethylene glycol as a gelling agent to make the viscous gel, and ammonia solution for maintaining the pH level of the solution. After the continuous stirring at magnetic stirrer for 1 to 2 hours at 70 degrees centigrade, as a result of combustion, we got the dried gel, which was further grinded and calcinated at 6 degrees centigrade for 4 hours to get the final molecules of cobalt oxide. We have also synthesized the same materials via co-precipitation method. So in this synthesis process, we have taken the 0.0 molar solution of cobalt nitrate in distilled water and 0.8 molar solution of sodium hydroxide that was added into the cobalt nitrate solution dropwise until the pH of the solution reaches to 10. As the pH of the solution changes, the color of the solution also changes, as shown in the figure. And after the 2 to 3 hours at magnetic stirrer, the precipitate was formed that was left overnight at room temperature. And after that, we washed the prepared precipitate with distilled water and ethanol several times to remove the excess impurities, which was further dried in oven at 60 degrees centigrade for 12 hours. And it was calcined at 600 degrees centigrade for 4 hours to get the final nanoparticles of the same sample. So to confirm the successful phase formation of the synthesized sample, X-ray diffraction studies has been performed. Here, figure A and B show the XRD patterns of cobalt oxide synthesized via Solvay autocombustion method and co-precipitation method respectively. Both the XRD patterns are in agreement with the standard data with JCPDS number 431003, and no impurity or secondary phase is observed in both the XRD patterns. We can get many information by the XRD analysis like lattice parameters, crystallite size, strain, and reliability factors. So for this, we have plotted the Williamson-Hall plots, and we have calculated the crystallite size by using Debye-Scherrer equation and Williamson-Hall equation as has been tabulated in the table. And from the table, it is clear the sample synthesized by a co-precipitation method has lower crystallite size than the other sample, and the strain is also decreased in this synthesis process. The Ritmel refinement of the XRD data has been performed using foolproof software, and the latest parameters, reliability factor, unit cell volume, and the space group of the synthesized sample has been tabulated in this table. To confirm the vibrational and rotational bands present in the sample, FTIR spectroscopy has been performed, and we have recorded this spectra of both the samples in the wave number range of 400 to 4000 centimeter inverse. The two sharp peaks in the low wave number region are attributed to the metal oxygen stretching modes, where the peak located at about 600 centimeter inverse accounts for the cobalt oxygen in tetrahedral coordination, while the peak at 630 to 550 centimeter inverse stands for the cobalt oxygen in octahedral coordination. And the other functional group present in the synthesized sample has been tabulated in this table. And these two sharp peaks confirms the successful spinel structure formation of the cobalt oxide. We have also recorded the Raman spectra of our sample to confirm the structure of synthesized samples. There are 5 Raman peaks that is clearly displayed in the figures at about 194 centimeter inverse, 79, 519, 680, and 688 centimeter inverse, corresponding to the F2G, EG, and A1G modes respectively. Specifically, F2G was attributed to the characteristics of tetrahedral sites, and A1G was attributed to the characteristics of octahedral sites. This also confirms the successful formation of spinal structure of cobalt oxide. To study the morphology of the synthesized samples, FECM images have been taken, and here figure A and B show the FECM image of the sample 1 that is synthesized by a Sogiel autocombustion method, and from the images it is clear that the sample has non-uniform morphology and a higher degree of agglomeration, and also the particles are forming from few nanometers to hundreds of nanometers, which can be seen in the figure C. The particles are forming from 20 nanometers to 50 nanometers.
Excuse me, Sharika, please present your conclusion.
Yeah, ma'am. Just one more slide. So the average particle size is 58 nanometers, and the EDX spectrum is used to confirm the elemental composition present in the sample. And these are the FECM images of the sample 2 that is synthesized by a co-precipitation method, and the particle size calculated from the particle size distribution curve is found to be 27 nanometers for this sample 2. So the conclusions: we have successfully synthesized cobalt oxide nanoparticles via Sogiel autocombustion and co-precipitation method. The single phase was confirmed by the axial diffraction patterns. The crystallite size are found to be 20 nanometers and 27 nanometers respectively, as calculated by using the Debye-Scherrer formula. The Raman and FTIR spectroscopy confirmed the successful formation of cubic spinal structure of cobalt oxide. The FECM images revealed the sample synthesized by a Sogiel autocombustion method has non-uniform morphology and higher degree of agglomeration, having particle size 58 nanometers, while the other sample has uniform morphology and lower degree of agglomeration with particle size 27 nanometers. Therefore, we can conclude the sample synthesized by a co-precipitation method has good structural and morphological properties, which can be used in various applications due to its uniform morphology and lower degree of agglomeration and the lower particle size. Thank you.
Thank you, Sharika. We move down to the next speaker, Dawood Ahmed Ansari.
Yes, ma'am.
Yeah, please.
Are my slides visible, ma'am?
Yeah, go on slide.
Yeah. So, good evening, all of you.
Hello,
I am
please.
Dawood Ahmed Ansari. I am a research scholar in the Department of Physics. And today I'm going to give a brief talk on the topic of investigation of structural, morphological, magnetic properties of pristine and co-doped cobalt ferrite and its supercapacitor applications. So here is the basic outline of my presentation. So first of all, I will start with the motivation behind the work. So our goal is analysis of structure and enhancement of properties of materials to make them useful for real life applications. And the current era is following the trend of device miniaturization, which has led to increased interest in the combination of multiple properties in a multifunctional device. So as we all know that the ever increasing demand of energy consumption is driving the scientific community to explore prospective materials for efficient energy storage and conversion. So in that regard, both lithium-ion batteries and supercapacitor are using spinel ferrites, which are of the formula MFE2O4, where M can be different transition metal elements like cobalt, nickel, zinc, iron, and others, as well as their nanocomposites for potential electrode materials. And the composites comprising of ferrite and rare earths are widely being explored in a bid to develop novel engineering materials without losing their existing advantages. So ample attention is being paid on the development of advanced materials via advanced synthesis routes in order to obtain controlled morphology that best suits the purpose. So in this regard, I have synthesized cobalt ferrite. Cobalt ferrite is a member of spinel ferrite family with inverse spinal cubic structure having space group FD3M. So it has polycrystalline structure and exhibits excellent physical properties because of its good chemical stability and thermal stability, and has non-corroding nature, and it is easily synthesizable and high mechanical stability and other advantages. So cobalt ferrite is a promising material that is being used in sensors, catalysis, EM wave absorber, magnetic recording, magnetic hyperthermia. Means it has a lot of in biomedical fields and in technological fields, and also in energy storage system. So the properties of nanoparticles are dependent on the chemical composition, annealing temperature, fabrication route, and the types and nature of dopants that are being put into the sample to alter their properties. So generally, the doping of cobalt ferrite with various rare earth element or transitional metal elements is observed to improve its physical properties. So we have, in that regard, we have investigated the effect of co-doping of nickel at cobalt site, and along with different transition metal elements, aluminium, copper, and manganese at iron site. So we have doped nickel at cobalt site in order to enhance its supercapacitive properties, and also the aluminium and other elements are doped at the iron site simultaneously in order to increase the electrical conductivity, which is our desirable goal. So here is a basic diagram of the cobalt ferrite structure. As you can see that the iron is surrounded by oxygen in two different ways. Half of the iron are occupying the tetrahedral sites, and half of the iron ions are occupying the octahedral sites. Similarly, the half of the octahedral sites are being used by the iron, and half are used by the cobalt. So the net magnetization is only due to the cobalt, because the iron are distributed antiferromagnetically between the octahedral and tetrahedral sites. So this was the basic introduction, and I have adopted the co-precipitation method for the fabrication of nanomaterials, because from this we can fabricate nanomaterials of desired morphology and size. We can optimize by using the amount of NaOH in the samples. So first of all, we took the stoichiometric amounts of the nitrates and dissolved it in water using magnetic stirring, and then after that we put NaOH in drop wise until the pH becomes 11, and after that formation of precipitate, we just wash them, and after drying it for 100 degrees Celsius for 12 hours, we perform the calcination at 600 degrees Celsius for 4 hours. That gives the sample, and these are the codings for the sample that I've prepared. So results and discussion. First of all, to confirm that our nanoparticles have been successfully synthesized, we perform the X-ray diffraction. So the X-ray diffraction patterns have been well matched with the standard JC periods of the cobalt ferrite, and all the important peaks have been matched and indexed, and no impurity peaks suggest that the sample has been successfully found without any secondary phase or impurities. And the crystallite size have been calculated using the Debye-Scherrer and Williamson approaches both. And along with that, we have also performed the rate-built refinement fitting using full prof software to fit the experimental data with the standard data. And along with that, we have found out that the crystallite size as calculated by the Debye-Scherrer method is 19 nanometer for the pure sample, and similarly for the different co-doped samples, it is 23 nanometers. And Williamson Hall approach, the crystallite size is just somewhat increased, like 24 nanometers and up to 43 nanometers for different samples. That is because we include this, and lattice parameters, unit, other parameters have been calculated out using the parameters that can be used for the structural study of the samples. Along with that, FTIR spectroscopy has also been performed over the samples, and the fingerprint region shows the presence of cobalt oxygen bond at 420 centimeter inverse, and around 591 the FeO bond are observed, which are the characteristic of the two functional group of the synthesized material, which further augment that the sample have been prepared and the in the desired phase. And other bands like OH and carbon oxygen, that may be because of the moisture present, that are also observed and assigned. Along with that, Raman spectroscopy analysis have also been performed, and it shows 6 broad peaks corresponding to the active Raman modes of the cobalt ferrite. And in this, the EG mode indicates the local distortion in tetrahedral sites, and A1G2 modes denotes the distortion in the octahedral sites of the cobalt ferrite, and it is because of the doping the distortion is produced. So it is actually the inverse spinal structure, but after doping the distortion is produced, so that the cation ratios change. So we can also calculate the cation inversion factor also from the Raman using the intensity of the A1G and A1G A1G2, A1G1 and A1G2 peaks. And the chi0 means normally spinal, and chi0, if it is lies between 0.1 and 2.9, it is mixed spinal. And for chi is equal to 1, it is perfectly inverse spinal structure. In our case, the values lie between 0.6 to 0.9. That means it is not completely inverse spinal. It has got distorted because of the doping. So it is somewhat mixed in the mixed spinal state. That we have also observed morphology using the field emission electron microscope. Average size, as you can see, that the molecules are the samples have are of the uniform shape and size, and the particle size have been calculated using the ImageJ software, and they are in the range of 29 to 38 nanometers for all the different samples. Along with that, the EDX spectra have also been recorded, which confirm the presence of the samples, and the stoichiometric ratios have also been calculated and matched, that are in accordance with the stoichiometric ratio that we have taken in the beginning. Along with that, elemental mapping also confirmed the uniform distribution of the different constituents all over the observed sample surface. So after that, since cobalt ferrite is a good magnetic material, we also tried to analyze the magnetic properties of the sample. So VSM was performed in the magnetic field range of 0 to 20 kilovolt, and we can see the maximum magnetization is observed for the pure cobalt ferrite. And after that, it is different, decreasing, and the values are different for different co-doped samples. But for the nickel and aluminum doped sample, the squareness ratio, we can see that the squareness ratio is 0.663. That is most reliable. Up to 1, it should be 1. That can be used for the application in magnetic storage recording media, and also in the magnetic switching application. So this material can be researched for that purpose also. After that, the main purpose of doping of samples was to enhance the electrochemical properties. So we have also performed the electrochemical test to confirm the supercapacitor behavior of the sample. The cyclic voltammetry was performed, and cyclic voltammetry was performed after we make an electrode of our sample and test it with the reference to we have tested it with reference to AgCl electrode in 6 molar KOH electrolyte solution in the potential window of 0 to 0.5 volt, and the highest obtained value is specific capacitance.
Get on to your conclusions. Yeah. Please.
Yeah, it is almost over. The highest value of specific capacitance is 1247 farad per gram, which is quite high as compared to the current materials, and the energy density is also quite high as compared to the super capacitors, and power density is also 2.625 kilowatt per gram. Good, and the GCD charging discharging curve have also been observed for the samples, and it also delivers impressive value of specific capacitance of 790 farad per gram at a current density of 10 ampere per gram. So these are the conclusions of my work. The pure and co-doped cobalt ferrite samples were successfully synthesized using the co-precipitation method, and the XRD and rate-well refinement methods were used to confirm the successful structure formation, and the different crystallite size have been calculated for all the samples. And the studies made on the FTIR spectra provide the confirmation of structure formation, as is evident from the presence of iron oxygen and cobalt oxygen vibrational bands, which are typical functional groups of the cobalt ferrite. And the Raman spectra further augment the phase formation, and other structural parameters have also been calculated from there. And the morphological studies done via FESM and EDX give detailed information about the size and nature of the synthesized nanoparticles, besides verifying the stoichiometry of the sample. And the magnetic studies yield that the highest value of saturation magnetization for pure cobalt ferrite samples is which gradually decreases with various doping in the pristine sample. And electrochemical characterization made on the cobalt ferrite prove its pseudo-capacitive nature, and high value of specific capacitance make it a strong candidate for fabrication of hybrid supercapacitors. Thank you.
Thank you, Raul. Thank you. Sorry, we'll have to move on to the next talk, which is by Dhanuka Shiva. Dhanuka, please. Please share your slides. Dhanuka Shiva, are you there or are you not there?
Hello.
Yeah.
Yeah. Good afternoon, everyone. I'm Shiva Sohanasri. We are at the Hyderabad College of Engineering for Women. We have performed a comparative study to analyze the zinc oxide nanoparticles that are synthesized using green synthesis method and the chemical synthesis method. Also, we have analyzed the particles that are obtained using in terms of their X-ray diffraction technique, structural properties, optical and microbial properties also. One second. So the presentation is all about the importance of the nanoparticles, the different techniques that we are used to synthesize nanoparticles, and the different characterization techniques also. Nanoparticles are those substances that will have at least one of the dimension in the nanometer range. And in the present scenario, nanoparticles are the future of our world, because there are a lot more applications of nanoparticles in different fields. This is due to their small size and tunable properties also. We can change the properties of the nanoparticles very easily during the time of the synthesis. The different applications of nanoparticles include in medicine, agriculture, electronics, and several other fields as well. We have some of the applications shown here. We have chosen zinc oxide nanoparticles as the subject of our study because it has a wide range of applications. It can be used in cosmetics, and due to its low toxicity and biodegradability nature, it is useful in biomedical applications also. It is used in anti-cancer drugs, and biosensors are also prepared using the zinc oxide material. It can also be used in the filtration of water in the water purification systems. And in addition to these fields, zinc oxide nanopowders can also be used as pigments for oil paintings and during the production of tires in the tire industry. And it can also be used as vulcanization acceleration activator. It means we can use the zinc oxide to speed up the process of vulcanization for any rubber substance. And it has a wide energy band gap of 3.37 electron volts. The change in this energy band gap of zinc oxide nanopowders, it will lead to the alteration of the optoelectronic applications, and it is transparent in nature in the visible wavelength range. It has a low refractive index of 2.05, which will make it easy to extract the light from any optical instrument. And this has also received the Food and Drug Administration's approval to be used in sunscreens as a material in one of the material in sunscreens due to its stability and due to its natural radiation. Zinc oxide's piezoelectric property will make it suitable for manufacturing piezoelectric devices using this substance. So the zinc oxide is the most desirable group of nanopowder. From the previous studies, it is understood that the zinc oxide's morphology, optical, and sensing applications in which we desire the applications. Our desire is that we want the zinc oxide particles to be of very small size. From the previous studies, it is understood that the method which we use for the synthesis of zinc oxide is showing a great impact in the properties that it is exhibiting, and that will in turn affect the area of application of the zinc oxide produced. So we have several synthesis methods that we use to prepare zinc oxide nanopowders to achieve the required properties for our applications. Now let us see the various applications of various methods.
There are several ways of synthesis of zinc oxide: physical method, chemical method, and biological method. And the preparation we use in green synthesis method, the group precipitation method, sol gel method, and microwave heating method are the chemical methods, and the green synthesis method is biological method. In synthesizing nanostructures through chemical methods, crucial process parameters are pH, reaction temperature, concentration of nitrates. Method is a simple and industry available technique. In general, in solution-based chemical or green synthesis method, initially metals are taken in the form of nitrates, chlorides, or sulfides. In our method, we have taken metal nitrate, that is zinc nitrate, is taken as the starting solution. In the process, we have taken metal nitrate powder and added to distilled water, and it is stirred with magnetic stirring, and NaOH base is added to it till the pH becomes 10, because pH has the high impact on particle size, crystal structure, morphology, and surface properties. After addition of NaOH, it releases the OH ions in the solution, and metal reacts with OH ions to form metal hydroxide, and further heating it converts into metal oxides. After formation of precipitation, it is taken out and rinsed with water for several times, and further it is done with filtration and drying, and after the calcination process, the zinc oxide nanopowders are prepared. And the salt process is the simplest method and has ability to control the particle size and morphological features. In this process, the zinc nitrate is taken as the starting element and it is stirred with magnetic stirring, and then citric acid is added to it as it acts as the strongest chelating agent, and then the base NH4OH is added to it.
Please present your conclusion. Nanoscience, please present your conclusion.
Okay, ma'am. And here the green synthesis method is the biological method. The influence of pH is very crucial in structural, optical, morphological crystalline effects of zinc oxide. Here we can see the peaks of different formation of zinc oxide in different methods. The height of the peak shows us the crystalline. We can see the different peaks due to the formation in different methods. Here we can see the deep analysis of the peaks. It is due to the strain in the material cross that change the peak in position. Here we can see the different zinc oxide particles at different pH. Here, due to the UV absorption and UV light spectra absorption and visible range spectra absorption, we can see the different wavelengths, and here we can see the energy gap formation in the 4 different nanomaterials, zinc oxide. The energy gap order is 3.2 for zinc oxide. Here we can see the 2 types of bacteria, gram-positive and gram-negative bacteria. When zinc oxide is added to these bacteria, there is a series of reaction which occurs in further studies. Conclusion: structural changes are observed. Strain is observed in the clean synthesis sample. Morphological changes are observed. Small changes in optical properties are observed. Peer back activities are observed for both gram-positive and gram-negative. Thank you.
Thank you, Nanoscience. Thank you very much.
Thank you, ma'am.
Yeah, thank you. Yeah, you can stop sharing. I just want to check there are 2 more speakers. Are they present or not? Ramesh. K. Ramesh is there. Hello, K. Ramesh. Are you there? Hello. K. Ramesh. Hello. Hello, Ramesh. Is Satish Kumar there? Satish Kumar? Are you there, Satish Kumar? Are you here? It's moving offline. Okay, Ramesh, I can see your name, but please speak. Are you logged in? Okay, there's one more Ramesh. No. Hello, Ramesh, can you hear me? Do you want to present? Hello, Ramesh, are you here? Hello, do we have Ramesh? Okay, thank you. So let's move now. Yeah, so now we have the valedictory function. And I would like to request head physics section to Professor Pasha. Please come to the dais. Some of them. Yeah. Till then, I'll sum up I will sum up the symposium. So basically, we had a very successful 2-day symposium conducted by the physics section. We had 6 invited talks and we had about 25 presented talks. A lot of students, everybody attended. We had various sections which ranged from astronomy, astrophysics, cosmology, atmospheric physics, lasers, not material science, biophysics. We had various areas which were covered, and I hope everybody has enjoyed it. The whole symposium has been recorded, has been live streamed on YouTube. So you can go to the IMC Manu channel, and under the Department of Physics, you'll find all the recordings of all the talks that happened in this symposium, right? So if you want to go through those talks, you're most welcome to go through that. Thank you.